Start. Okay. So thanks for the opportunity to talk about BigQuery and data science. It's like two of my favorite topics. So this is a great conversation to be having, and I'm looking forward to chatting after we get through some of these slides here. So basically what I wanted to do was just talk about some things about BigQuery that might not be as well understood as some other things with regards to like how we work with other relational databases, especially for data scientists, data engineers who are used to working with other tools. Let's see, there we go. So first, I just want to give a little overview. BigQuery is a serverless data warehouse, and it's a service that's provided by on Google Cloud. They do have a version of BigQuery that can run in other clouds as well. It's called Bigquery Omni, but most of what I'm talking about now is probably applies mostly to BigQuery hosted on GCP environments. And one of the great things about BigQuery is that it's petabyte scale. So it really scales up really, larger than most data warehouses, and it really isn't we don't have to like think a lot about scalability. I mean, it's already built into the platform. Now it does use SQL, and it uses ANSI standard SQL, so it's it's very easy for a lot of us to like pick up and work with. But one thing to keep in mind is it's not a relational database; it's an analytical database. So a lot of things we're used to in databases like Postgres or MySQL aren't available in BigQuery. And these are basic things like indexes and foreign keys. That's just not how BigQuery is built. And BigQuery is really built for speed and large volumes of data. There's also some other things. They've baked in some other things that are really kind of interesting, like Bigquery Ml, which I'll talk a little bit toward the end of the talk. That allows people who know SQL to build machine learning models. So you don't have to export data, you don't have to code up something in Java or Python. You can actually do it with SQL. There's also the Bigquery BI engine, which gives you really low latency in-memory analytic operations, and Bigquery GIS if you're doing some really complicated geographic information processing. So I kind of alluded, I mentioned a little bit about some of the differences from BigQuery, but the differences are a lot more fundamental and deeper than just the few things that I mentioned. So the first thing that's really different about BigQuery relative to relational databases as they've existed for the past several decades is that BigQuery has separated out the sort of the compute portion and the storage portion. In the past, when we did data warehouses, we would sort of vertically scale, get big servers with a lot of RAM and a lot of memory and a lot of CPUs, and then also a lot of disk space, because the compute and the storage was tightly coupled. And the problem with that is that sometimes you maybe need more CPUs, sometimes you need more storage, and they don't necessarily grow, or your demand for both is not necessarily tightly coupled or tightly correlated. So one of the things that the developers of BigQuery did was they separated out the storage system, and as this diagram shows, the storage system is based on Colossus, which is Google's global file system. It was actually GFS, or the Google file system, was the first generation of their distributed file system. Colossus is the second generation. It's more reliable than the earlier version. Also, a lot of metadata that's needed with BigQuery is stored in Spanner, the global relational database. Now, the other piece of the main piece of the puzzle is the compute platform, and that includes a couple of components. There's something called 𝗲𝗏, which is the query processor, and Borg is the job sort of coordinator. And you might have heard of Borg because it's a predecessor to Kubernetes. So a lot of the ideas and sort of learnings from Borg were applied in Kubernetes as well. And then the other key thing with regards to BigQuery, and this does not apply to BigQuery Omni, the big difference is that on the Google infrastructure, we have access to a petabit network called Jupyter. And so it's very fast networking. So whereas in other clusters, like if we were to set up our own database and have a cluster with just sort of conventional networking equipment, we'd probably spend a lot of time thinking about rack awareness and distributing our workloads so that they, as much as possible can be done on a single rack, and there's not a lot of data that needs to be shuffled back and forth. But with Jupyter, that's much less of an issue. So it's not a problem if you're going out to Colossus, a different storage system, and you're doing computes on a bunch of servers in a rack somewhere else, because we don't have that same level of sort of latency with the petabit network. So those are sort of the three key components: the compute part, the storage system, and then the very high-speed networking. So a little bit more about Dremel. Dremel runs basically a multi-tenant cluster. So that means that your queries, my queries, other people's queries, they're all being run in Dremel. They're all being run by on the same cluster. And what Dremel does is it takes our SQL queries and maps them into execution trees. So it breaks down the SQL into basically chunks of work that can be done. At the beginning, it starts with retrieving data and then sort of doing work in between, like doing aggregation or doing filtering or anything else that we want it done sort of computationally inside the SQL statement. Dremel is taking care of that. Now, Dremel is organized into a tree. The leaves are the bottom of the trees. Those are called slots. And slots are the things that actually read data and perform a computation. And a slot is basically it's like an abstraction of a certain amount of compute and a certain amount of memory. And so we can think of it as not necessarily like a container, but it's a unit of computation, or like a unit that we can do work with. And by default, like when we start up an account and have a project in Google Cloud, we get by default a maximum of 2,000 slots. So we have a good number of slots to work with in general. You can also pay for more slots. If you're a big heavy user and you need more, you can purchase a committed number of slots. Now, as I had mentioned, sort of the inner nodes are of the tree actually perform a lot of the work, like the aggregation. So if we're doing things like counts or doing moving averages, that's the kind of operation that's performed on the inner nodes. And the slots themselves are dynamically allocated to queries. And one of the things that is important about Dremel, since it is multi-tenant, is that it's able to maintain fairness. So I can't run a job that consumes, too much of the resources in BigQuery, as opposed to, say, having, an old Unix server where I might run a job and, have a very low priority, or I have high priority, so I keep hogging all the CPU. That kind of thing doesn't happen with the jobs that are scheduled on BigQuery. And here's a diagram to show sort of visually how these pieces relate. So basically at the bottom of this screen, we have Colossus. And Colossus, again, that's the file system, the global file system. And that's where storage goes in Google Cloud. So if you're using cloud storage or Bigtable, BigQuery, eventually your chunks of data that are being persisted, they're being written out to Colossus. And so this is an example of Google investing heavily in a very foundational technology and then reusing that over and over again in different use cases. Colossus is also used with Spanner. And then on top of Colossus, or really in between Colossus and the Dremel nodes, the Dremel servers, we have the Jupyter network. And then we have basically the tree of nodes that run are managed by 𝗔𝗏. And those, again, the leaf nodes are the things that do the work with like fetching data. And then the mixers or the inner nodes do a lot of the computation. And then there's a root that sort of controls the whole job. And all of this is orchestrated across multiple tenants by Borg. Just to give you kind of a visualization for Colossus. So when we have, when we're writing data to the persistent storage of the Colossus file system, it's being written, or some master or primary node controls this cluster. And there are multiple clusters for high availability in Colossus. That was one of the big changes with regards to the Google file system. The first generation is it had a single point of failure, but that's no longer the case. And then within Colossus, there are these things called chunk servers. And basically, a chunk is an amount of data. It's like a block of data, analogous to the idea of writing a block to a disk. Well, in Colossus, you write a chunk. And so Colossus handles a lot of important operations like replication. So when a chunk is written, it's actually written multiple times so that we have high durability and high availability. Colossus also handles encryption. Encryption is actually handled at multiple levels. But one of the things that when you're writing data to Colossus, one of the things is that happens is that your data is encrypted. Each chunk gets encrypted with a key, and that key is encrypted as well. That's called envelope encryption. So a lot of this stuff, again, this is like a fundamental part of the Google infrastructure, which is one of the reasons it has as many security mechanisms as it does across so many platforms, is that they build really foundational pieces and then keep reusing them. So again, like Colossus has some important encryption technology in there as well. So it is a distributed storage system. I mentioned the replication and recovery. And the other thing about Colossus is it's essentially not something we need to manage in the sense of allocating blocks for a certain amount of storage. We just go get it as we need it. Now, Jupyter, I had mentioned, is Google's networking technology, and it's actually a switch. It's like there's hardware that they actually built. So this is unusual. A lot of Google's technology, like Andromeda, the virtual private cloud, sort of layering and things like load balancing, the dynamic load balancing, those software functions are implemented in software. But Jupyter is actually a physical piece of hardware, and it's their switching device that, again, is at petabit scale. And it's really important for that Colossus to the compute cluster communication. Again, so yeah, very little need for rack awareness. We don't have to think in terms of trying to minimize as shuffling across nodes as much as we used to. Now, Borg is, I think I had mentioned, it's sort of the predecessor of Kubernetes. And that's the thing that manages the mixers and the slots, the actual compute resources, and how jobs are run and scheduled and things like that. So that's sort of a background on why BigQuery is different. And if you're familiar with things like databases like Postgres, you're probably used to thinking in terms of data blocks being allocated and write-ahead logs and being able to recover and having things like indexes automatically updated. BigQuery doesn't have that kind of stuff. So when we work with BigQuery and when we do data modeling with BigQuery, we really have to rethink or sort of unlearn some of the techniques we use with traditional relational databases, because the architecture is so fundamentally different. Those differences in architecture really require us to have differences in our data model design patterns. So one of the things we want to keep in mind is that BigQuery uses a columnar format, and basically what that means is when it stores data, it stores data in a row orientation, a column orientation. So all of the, we might have data from tens of thousands of rows. one column's worth all stored together, which again is another difference from the way many relational databases work, which are row-oriented. So you store a whole row together. And row orientation makes a lot of sense when you're writing applications and you want to say, go look up a customer's account or something like that, or an order. You want the entire order and all the attributes. That's not typically the way we work when we're doing analytics. We typically look at, a small number of columns. Maybe we look at time and a couple of metrics, and we want to compare those across a large number of rows. So capacitor is really useful in that sense, because it's specifically a columnar storage format. Now, there are other columnar storage formats, but there are some features of capacitor which lend themselves, especially to the way Bigquery is designed. So it supports semi-structured data, so we can have records, record structures and arrays within our columns. So the nested structures are things like JSON structures. So it's very similar to JSON. We can structure those hierarchically within Bigquery, within a column. And we can have repeated fields, so we can have arrays, essentially. And one of the things that's, or one of the advantages of capacitor that isn't necessarily the case with other columnar formats is that you don't have to read the parent column to produce a nested structure attribute value. There's enough metadata in the capacitor format so that if you're down deep into the lower level hierarchies of a nested record, you don't have to have all the information about all of the outer layers as well. So that's one of the reasons that capacitor is such a good choice, and it was developed specifically to support this kind of thing, but it really helps with the performance of Bigquery. And it also, because we're doing columnar storage, and oftentimes columns, especially those with low cardinality or very few distinct values, they really lend themselves to high compression ratios. So I just want to show you an example of a nested field. And what we have here is a public data set in Bigquery. If you look for sessions, Google Analytics sessions, there is a data set with a table with Google Analytics sessions for 1 month from 2017. And what you'll notice here, for example, is we have some of the columns like the total, traffic source, device, geo network, and so on. Those are all records. And that means that they are structures with basically a set of key value pairs. Now, some of those, like custom dimensions and hits, are also repeatable or repeated. And a repeated field is one that is essentially can be an array, or it is an array, and you can have multiple elements in that array. So you can have both structures and arrays. So you can get fairly complex in how you nest things and use arrays in ways that allow us to avoid having to do normalization. And that's really probably the hardest thing to get used to with Bigquery. If you're used to working with, say, Postgres or Oracle or SQL Server, and used to using third normal form data models, that's really not the way we build from scratch. If you're designing a data warehouse from scratch in Bigquery, you're more likely to use and get better performance from using nested fields. And here's just an example of expanding out a record with a repeated field. So the columnar storage is really important. That helps us sort of retrieve data in a very targeted way. And that's sort of, we can think of it as like vertically, like we're getting a bunch of the same column from a bunch of rows. But we also want to be able to grab a group of rows to work with without having to scan too much. And that's where partitioning comes in. Now, what partitioning does is it basically breaks up a large table into smaller chunks. And so, for example, we could break up a large table into 5 partitions. And this is helpful because if you know where your data is located, if you can quickly figure out which partition has the data you're looking for, then you can go directly to that partition. Because Bigquery spends a lot of time scanning data. That's sort of its secret mechanism. It's very fast at scanning data in parallel. And that's how it can get away with not having things like indexes. So you don't have to go to an index to look up a value to get an address block to go look up your actual data. With Bigquery, with enough resources, compute resources, you can scan very quickly large volumes of data. And so Bigquery has opted to go for full scanning over indexing. Now, just because it's really fast at scanning doesn't mean you want to scan a lot of data. If for no other reason, then Google charges based on how much data you scan and how much data you store. And also, if you stream data in, if you ingest streaming data, there's a charge for that. So those are the three sort of components with regards to charges in Bigquery. So we have a financial incentive to minimize the amount of data we're scanning, but then also just performance-wise, the less we have to scan, the faster our queries will be. So what we do, the way we use partitioning is that we partition individual tables, and the tables get segmented into these smaller blocks, and we call those partitions. And as I mentioned, it improves query performance because it reduces the amount of data we have to scan, and it also lowers our costs. There are a few different ways we can make partitioning decisions. One way is by partitioning by ingestion time. So as the data gets loaded into Bigquery, we can like partition by that day. So any data that came in after midnight tonight is in a partition for today's date. And at midnight tonight, there'll be a switch and a new partition will be automatically created. And tomorrow's data, starting at right after midnight, will go into that partition. So this is really useful if you want to use the ingestion time to determine a partition. And so, for example, if you have sales data and you want to organize that by partition, using date, the time it's ingested works really well. You just have to be careful about late arriving data. So late arriving data, say my sales data for today, if it should arrive at say 1 a.m. tomorrow, then if we partition by ingestion time, my sales data for today might end up in tomorrow's partition. So that's just one of the sort of factors you want to think about. Now, partitioning by ingestion time, partitioning by ingestion time creates a pseudo column called _partition time, and you can use that in your where clause, just so you can, again, filter where partition time is equal to, and then give it some date. And because partition time is a date-based timestamp, and yeah, we use that typically in our where clauses. Now, we can also partition by some other date or timestamp. And this is based on data that is actually being ingested. So it's not when the data arrives, but somewhere in the data set, there is a timestamp or a date that we can use for partitioning. And we will oftentimes we use this kind of date timestamp partitioning with things like IoT sensor data, where we want to basically partition the data based on the time the event occurred. So if I have sensors and I'm collecting, say, temperature data from refrigeration units, and I have data that's just streaming maybe every minute, every couple of minutes, and I want to be able to look at the time or look at data based on what time the sensor reading was taken, and not have to worry about what was the network latency before it got to Google Cloud, and then was it in some kind of ingestion queue? Was it sitting in PubSub for a little while before we finally got to it and it was ingested? So, so for cases like that where you want to work based on event time, you can use the date timestamp partitioning. Now, because we're using one of the columns in the data set, we don't have to have a pseudo column like partition time. There are a couple of partitions that are created, though, when we do use timestamp or date partitioning. There's a _null_, and this is useful when there's a null in the partition column. So if that were to happen, the data would be put into the null partition. And then there's also an unpartition. which is when the date ranges are out of whatever range we are expecting and we've defined for the table. So it can go into the unpartitioned table. Excuse me, unpartitioned partition. And then the final way of partitioning is integer range partitioning. So the partition column must be an integer data type. And the column can't be repeated. So this can't be an array of integers. It just needs to be a single scalar value there that we can partition on. And that scalar has to be an integer. Oh, this probably isn't as important anymore, but you can't use legacy SQL to create partition tables. Legacy SQL, as the name implies, was around first, and then ANSI standard SQL came later. And there were some differences, and I don't know of a lot of reasons. I don't have any particular reason to use legacy SQL unless it's just like old code. So ANSI standard SQL, this shouldn't be a problem with regards to partitioning. Now, there's another technique that has been used in the past and across really all kinds of databases. This isn't just Bigquery. It's called sharding. And it's very similar to the idea of partitioning. But instead of using partitions in one table, you create a table for each day. So rather than you use a partition, we actually create separate tables. And we do things like create a table name like IoT sensor data underscore, 220412. And that becomes a table. And there are many tables with similar names. And whenever we want to go across, say, these time periods, we do union queries and we scan these multiple tables. Now, partitioning is preferred over sharding, just as a good practice. Partly there's less metadata to maintain because each of those individual tables in the sharding approach has its own metadata and it has its own access control mechanism. Management issues, so we have to check authorizations each time we check different tables. Whereas if we have read access to a table, then we have read access to partitions in those tables. So there's less overhead when we're working with partition tables than if we were working with sharded tables. Now, one thing we can do is when we create a partition table, we can indicate at table creation time that anytime someone queries that table, they have to use a where clause. And that where clause has to be based on the partition key or how we're partitioning. And it gets specified at the table level. And it requires a where clause with the partition column referenced in it. Now, there needs to be at least one predicate that only references the partition column filter. And so, for example, if your partition column is called partition ID, you could have a where clause like where partition ID equals ABC. You could also have a partition or a where clause where it's like where partition ID equals ABC and foo equals bar, some other column. But so and will work, but an or operator won't work because it's possible that we could have something satisfy that condition that is part of the other part of the or clause and not part of the partitioning key. So you just want to just keep in mind that you want to have, anytime you require partitioning on a table, you're forcing everyone who queries to use a where clause that references the partition key. And that's one way to help control costs. It's not necessarily a bad thing if you want to help people not run up your BigQuery bill. This is an easy one to easy technique to use to help with that. Now, clustering is another table sort of property or feature, and clustering allows us to store our data in a sort order within our blocks of data. And this is really useful because it can improve performance on scanning and also with aggregate queries. And again, when you use where clauses with the cluster columns, you can sort of narrow down the range of what BigQuery has to scan. So again, we're back at this idea. BigQuery is really good at scanning, and we can sort of reduce the number of partitions, but even within a partition, we can get an even narrower range by using clustered tables. Now, you might wonder with clustered tables, what about new data that gets inserted that might be in the middle of a block of data? And that is a problem. It can happen. It's not really a problem. It's just a feature of the way systems work. So as new data is added to the table, it may be out of order initially, but BigQuery in the background is reclustering. So we don't have to think about it. So most of the time, this isn't an issue because oftentimes we write like time-oriented data. So we're not going to go and write data to yesterday's partition in many cases in a data warehousing environment. Also in BigQuery, we don't typically update records once they exist. You know, BigQuery is almost always we're adding more data. We don't really do a lot of updating. So this kind of automatic reclustering is often, you know, it works well. And so we don't really need to think about performance issues with reclustering overhead. One of the features I find most interesting in sort of the newer feature releases around BigQuery is the fact that we can now do machine learning inside BigQuery using SQL. So what this allows us to do is that we can create models right in BigQuery using SQL statements. Google has expanded the data definition language of SQL in BigQuery to include things like create model, and allows us to create different kinds of models. Now, there are a number of different kinds of models, like, of course, like linear regression is widely used, and that's relatively easy to set up. It also supports binary and multi-class logistic regression, k-means clustering. You can do time series forecasting. Also XGBoost, which is highly performant. And then there's others. I didn't have enough room on this slide to put all of the different types of models. So there's some advantages. So really the big advantage is now all of a sudden you can, if you know SQL, you have the tools available to build machine learning models. And that's incredibly like democratizing of machine learning. It's like, okay, now all of a sudden a lot of people have access to this. You don't have to be a programmer and know Python and be able to use like scikit-learn or like TensorFlow or use Java and use some other libraries like that. And another big one is there's no need to export data. You don't need to push these out to files and then read from the files. You actually get to take advantage of all of the BigQuery infrastructure for dealing with, you know, petabyte scales of data. You get that sort of for free with your machine learning algorithms. So here's an example of a create model. And the syntax is interesting. I mean, it's basically a create model given a name of a model. And then you specify a list of options. And those options will vary depending on the kind of model that you're building. Now, in this example, we're building a linear regression model. So we need, for regression, we're trying to predict a single value. And so we need to be able to identify, well, what value are we trying to predict? And we specify that using an option called the input label columns. And so we're interested in weights and pounds. So this regression is trying to predict baby weights based on other characteristics. And then we have a select statement, and we're going to select a number of columns from our data. And those are basically that's the information, what we're trying to predict, plus a bunch of other attributes that we think might be relevant to influencing, in this case, the weight in pounds of babies. And then we pull that data from some table or view. And in this case, there's a where clause where the weight in pounds is not null. So we don't want to bother with anything where we don't have a value that we can learn from. And we're going to generate a random number between 0 and 1. And we're going to take about every 1 in 1,000 of the rows in this table. That's what the rand less than 0.0.001. That's just a way of doing essentially random sampling. And it allows us to take a small subset of all of the rows that are in this big table public data set. Now, once you've built your model, then you can actually use it to make predictions. And with that, again, we're back to a select statement, and we want to select, the predicted weight, because that's the thing the value we're trying to predict. And then the from clause is an ML predict function, or a call to an ML predict function, where we specify the model that we want to use. And in this case, it's the model we just built. And then we want to pass in the same columns that we use to train the model, with the exception of what we're trying to predict. We don't have that, so that's what we're trying to predict. And then you have your from clause, and if you want to select your data, in this case, they're selecting from a single state in the US called Wyoming. So this is how we can now do machine learning in BigQuery. So if you've worked with other machine learning tools like scikit-learn and Python or TensorFlow, you probably get a sense this is a lot faster than setting up models and doing a lot of the work, especially like the data massaging work and things like that. With ML in BigQuery, we get to take advantage of all the work that was already done to get the raw data organized and cleansed and transformed and put into the right kinds of structure. So now we can really use it both for analytics and data warehousing, as well as for machine learning. And then finally, as data science people, data engineering people, we're always thinking about performance tuning. And again, with BigQuery, it comes down to the architecture. And so here's an example query. If you haven't used BigQuery before, this is the Bigquery Console. So if you want to work interactively, this is kind of like working in pgadmin and Postgres, or MySQL Workbench in MySQL. And so here is a case where I'm just querying some data. This data has to do with bike rentals, short-term bike rentals within a city. So if you pick up a bike, rent it, ride it to another part of the city, return it to a different station. There's data about that in BigQuery public data sets. And so one of the things you can do is, as you're building queries like this, you get a lot of details. Now, we have the results here, sort of at the bottom of the screen. We see results, but there's also a tab called Execution Details. And if we look at execution details, what we see is information about the execution tree. And if you remember back to earlier in the talk when we were talking about Dremel and how Dremel breaks things down into these different stages of execution, well, in the execution details, we can see those different levels. And for each level, we can see how long BigQuery is waiting. So if it's waiting for data, how much data it's reading, how much time it's spending in compute, and then, how much time it spends reading, how much time it spends computing results, and then how much time writing. And what we want to do is watch out for things that are really skewed, or if there are long times on the joins, or there's a large number of reads. Maybe we're reading more data than we need to in the join operation. So one good practice is to reduce as much as possible the data sizes before you do the joins. And so with BigQuery, you get access to a lot of the, this sort of basic information. Now, this is a lot different from tuning queries in relational databases. In relational databases, the query builder, query execution plan builder, builds a complex plan, or it could be complex based on the query, and it might take advantage of different kinds of join algorithms, different kinds of indexes, different indexes in general, different ways of filtering and partitioning. And people who work in relational databases have spent a lot of time to optimize and come up with methods for figuring out really good query execution plans. We don't need to do that in BigQuery, because BigQuery is really, it's like a one-trick pony. It doesn't do a lot, but what it does, it's really good at. And basically, and what it does is it scans. It scans data in parallel and performs aggregate operations and can build single result sets. So that's why the kind of detail we get is more generic. It's not specialized to each query. You will see the same kind of outputs. Now, the number of stages will vary, but the wait, read, compute, and write time are standard across anytime you look at the execution details. So that's kind of wraps up the performance tuning with BigQuery. And there's a lot of, excuse me, I shouldn't say a lot. There are a number of well-established kind of best practices with regards to BigQuery and data modeling. Again, those are relatively simple once you understand, and they're simple and logical once you have a sense of how the architecture of BigQuery is organized. So just one last thing, just to summarize, the key sort of takeaways from this talk are that when we work with BigQuery, we are scanning in parallel, and it's a distributed system. So we want to design for scanning in parallel. And this is especially, I say this for people who are like me, who started, came to BigQuery after working for many years in relational databases. We want to partition to minimize the amount of data that gets scanned in large tables. If you can use clustering to further reduce the amount of data that's scanned, and that's now joins are very common, of course, in normalized databases, but joins can require shuffling across slots. And I know I've been saying we don't need to worry about shuffling data because Jupyter's so fast, and it's true. It's sort of like we don't need to worry that much about scanning because BigQuery, the scanning mechanism, is so fast. But if you can avoid it, it's better to not shuffle the data. Like one of the things in the execution plan showed like bytes that were spilled over to disk, so that couldn't be stored in memory, and then bytes that were shuffled across slots. So you don't want to move a lot of data across slots if you can avoid it. Now joins can drive that kind of behavior. So the way to minimize that is to denormalize using nested and repeated fields. And the reason for that is that then data that's related is kept together. So if we have an order table and order details with a bunch of rows, each individual order and its details are basically kept in the same sort of chunk. So when you go out to Colossus and grab a chunk of data, it's going to have the order as well as the order detail information. It doesn't require as many I/O operations to get all the data you need. So, and this is why we denormalize. This is why we use nested and repeated fields in BigQuery. So also, just so that kind of wraps it up. If you want more details, I do have a course on Udemy, which is a prep course for the Google Cloud Professional Data Engineer certification. There's more details about BigQuery in there as well. But so that wraps it for what I was hoping to cover. I'm very happy to take questions if anybody has questions. But thank you. This has been great. I really have appreciated getting a chance to talk about this.
There is a question in the chat. It says, is there a metric or indicator that tells us when it is necessary to partition, or should we always partition?
That's a great question. In general, partitions should be at least 1 GB. So if you're thinking about partitioning and you have a small amount of data and you know, say under 10 gig, it's probably not needed, especially if some of those partitions are going to be much less than 1 GB. But in general, partitioning is usually something we want to do, but except when the tables are small. And the 1 GB per partition is generally the way to kind of decide. Yeah, that was good. I should remember to mention that. That's a good question.
Thank you, Dan. I have another question. when partitioning tables in BigQuery, can I have more than one table to, more than one column to partition?
You use one column because it's going to be one column. It will be either the ingestion time, which is sort of like a pseudo column. It will be one of your timestamp columns, or it'll be one integer column.
But yeah, I can choose only one, right?
Yeah. It's not as flexible as partitioning like in Postgres, where you can have a couple different ways of partitioning, and yeah. Also, let's see. A question came up in chat. Can you share with us how BigLake integrates with BigQuery? That's another great question. BigLake was just announced, I think it was last week at the Data Summit, the Google Data Summit. And BigLake, it almost like extends BigQuery. So I was talking about data that's stored in BigQuery, but BigQuery also supports federated data. So if you have columnar data, say stored in Parquet files or Avro files in cloud storage, you can query those too. And now with BigLake, it's making it easier to do that kind of federated querying. So BigLake is like taking BigQuery and then bringing some of its query features and metadata management to a broader array of data sources. So it could be cloud storage. I don't know enough about BigLake. I don't know, for example, if the data can be in AWS S3 storage or Azure cloud storage. But it's in a sense, it's like BigQuery is still like the brains of the operation, but with Data Lake, we're getting access to more data. Let's see, here's a question. Is there a way to track all queries performed by a user in order to get metrics from data customers, which are top user queries? Yes, there's like info query, information schema, and I can't think of the other things, but yeah, like for example, when you're working in the Cloud Console, you can get a history of all of your project queries and things like that. So it is definitely available, and I will try and remember where that is. And maybe I can post something. It'll probably come to me tomorrow. I'll post something on LinkedIn to that, to David, or I can respond to this. I'll find some place for us. For data exploration, do you recommend using BigQuery or data catalog for data scientists and analysts? Well, BigQuery, you might want to use both. Data catalog is also part of BigLake, and data catalog is for metadata. So that's really useful when you have like information about columns and what business domain they're in, like if this is finance data or legal data or some other data. So data catalog is a tool for helping you find data, but the data you're looking for, it might be in cloud storage or it might be in BigQuery. But I would say from a data science perspective, BigQuery is really good for loading up data, even if it's raw data, doing the initial data transformations and preparing the data and building your feature sets, and then using BigQuery for either the analytics or the machine learning. Let's see, I just want to make sure I don't miss anybody's question here, and I'm sorry, do you know trained model for BI tools? Oh, can you call trained models from a BI tool, for example, Data Studio? That's a good question. You can, I don't know, you could call the model and then take the result sets and pipe that to Data Studio. I don't know if you can how you would in Data Studio make the call. That's interesting. Yeah, I don't know. I'll see if I can find somebody. I don't do a lot with Data Studio, so I'll see if I find somebody who might know that. I know with tools like Looker, you have more programmatic control. So I'm certain you could do it from Looker, but I don't know about Data Studio. How can we reduce data shuffle across the cluster? Well, the big things are avoiding joins and using nested and repeated fields so that data that is related together stays together. Also, you want to avoid doing order by on a very large data set. So if the data is really distributed across slots and you want to do a big operation and you want to return a large data set and you have an order by right at the end, you're going to end up, you may exhaust your resources. You may find out you don't have enough slots to do the ordering. I've run into that. So I would say those are the two big things. Watch out for joins and denormalize if you can, and be careful with like order by operation. Things like order by operations where you have to move a bunch of data together. Does BigQuery have a time travel feature like data like? Yes, there is a way, I forget the column, you can do like a as of time thing. Again, I'm just gonna make a quick note about that one so that, I forget what it is, but there is like a time travel. And then the query use statistics. Okay, I will see if I can get an answer to that one as well. Is there any way to optimize joins in BigQuery? God, I hate to say no, because it's like, I don't think so. Like optimizing optimizing gives works if we have options, and so we're trying to choose the best option. With BigQuery, we don't have options because all BigQuery is going to do is scan and shuffle and do compute operations. So the only thing we can do is avoid the joins by denormalizing. And then also if you do need to use joins, use small tables. Actually, you probably could, if you use the first table in the from clause, you typically want that to be your largest table, and that'll be the driver. That could, and then if you have joins and you have joins on smaller tables, that could reduce the amount of shuffling. But like all things, in databases and computer science, it's like do experiments. So if you do have a really large table and you have some joins, definitely try the different orderings, but I would say start with the largest table first in your from clause and then work your way down. Let's see. Given that denormalized data is preferred in BigQuery, does it mean that it's not recommended to use the star schema? That's interesting. I've heard from Google, people at Google, different things at different times. Early, like years ago, people would say, yeah, don't use star schema. But more recently, I've heard people, Google has documented as a good migration practice, if you have a star schema, like on premises or in Teradata or Oracle or something, then the suggestion is keep the star schema, bring it into BigQuery as is, and then if you're not getting the performance you want, then change it to a more denormalized model. So it depends, what you should do if you have an existing star schema and you're migrating to BigQuery is basically just try and do the easiest thing and the fastest thing, which is lift and shift. Just bring it in and don't change the model. If you're starting new, then you're probably better off starting immediately with denormalized. Now, with star schemas, there's this concept of a slowly changing dimension. And one of the things that we get with BigQuery, and I forget which type it is, but basically, as soon as we write the data, we're writing values, say like a country code. And so at a certain point in time, we write the country code that exists at that point in time. Now, if ISO comes up, sometime in the future and changes the country codes around, and we start writing these new country codes, our old country codes don't change. Now, in a star schema, if you did a query and you queried like the country code dimension, and we overwrote the old value with the new value, even your historical data would show the new value. So if you're really tied to that kind of that type of slowly changing dimension, then that would be a reason you want to think about whether or not you want to use star schema still. But other than that, one thing, I can't think of something in star schema that you couldn't get out of BigQuery and it would be wouldn't be a problem. Like you could always go back and update your old data if you wanted to each time you had to update a slowly changing dimension. But that's a lot of work, and it's not really how we use BigQuery, but you could do it. So I guess, yeah, the short answer is I wouldn't start with the star schema, but if you have one that exists, definitely bring it over. Can roles be configured to access specific tables? Yes. And can tables or columns be classified as under column? Yes. There is column level security, and thank you. Yeah, there is some on that, and I'll post some links to that. There's some good write-up in the Google documentation, but I should add that to when I talk about BigQuery. That's a good question too. And it's type 2 slowly changing dimensions. Thanks, Miguel. All right. What about schema evolution? Schema evolution is hard. So as you're ingestion, like you're ingesting data and it's changing, there's a couple of things. I don't have, this is a hard problem. And so as your input data starts changing, how do you adapt to it quickly? And one option, and the way we sort of always did it in the past, was do it manually update table schemas, alter tables to add new features. BigQuery now supports storing JSON data type. So you could be storing, at least in your initial load, like your raw data load, storing as JSON structures. And that usually works pretty well because then you can programmatically analyze the schema. And then also a lot of formats like Avro, there's a lot of metadata about schema. If you have information about the changes in the schema, like if you're constantly watching, then you can programmatically manage. But I don't have any good practices on that one. But again, let me just make a note of that one on schema evolution. And that's a great question. In fact, it was one I was dealing with a couple of weeks ago with an IoT application. Yeah, that's not a well-solved problem, at least from what I've seen so far. All right, I think that may be all the questions. Well, thank you. This is really, these are great questions. And I've got a list of like 4 or 5 things here to look up, and I would be happy to share those. And I appreciate these questions because it helps me understand, things that are missing in talks and things like that. So yeah, and if I can ever help you in the future, feel free to connect with me on LinkedIn. Message me if you have questions, questions like this, or just, anything, broad questions or career questions, but I've been doing this a long time, so I'm happy to talk about that. But yeah, definitely feel free to message me on LinkedIn if I can ever help with anything. And thank you to David for hosting, and this has been a really enjoyable evening for me.
Thank you, Dan, for being our special guest. This is the first time that we have an event like this, being the English, not our natural mother language, but the passion that the community has for Google Cloud, and especially for data warehouses and all things data related, is not gonna stop us. Be sure about that. And I hope that you will get the inputs necessary for the next editions for your upcoming books. I hope to see there the new release, the Big Lake in one of your books.
Thank you. And soon, I hope. Right. Well, thank you again. It's been great.
Daniel, do you want to say something?
Thank you so much, Dan, for your explanation. GCP is a passion for everyone. I know we need a study group for GCP. And that's all. Very, very interesting.
Well, I'm so happy to hear that. I hope it's useful and helpful. And yeah, I hope to, maybe we can do this again on some other topic that's related to data engineering sometime.
Please, we have this stage just prepared for you, and you know, we will be very happy to have you again someday.
Yeah, thank you. Thank you. All right.
Okay.
Well, thank you. And have a good night, everyone.
Good night. Bye-bye.
Goodbye.
Okay, what comes now? Do we switch to Spanish?
Yeah, we can switch to Spanish.
Well, I know we have still around some people that are don't talk Spanish, but if you're listening to this, if you were listening to this talk, I just wanted to say thank you for being here, for being part of this, and you can feel free to join maybe the Telegram or follow the LinkedIn page or follow us on Twitter, or if you want something we can discuss in the groups or in the Telegram or whatever, just feel free to reach out, right? Muchas gracias a todos.